Pleasure to take you to our next presentation, which is going to be on-farm data trust and provenance. And I'd like to introduce Volkan Diaglu, who's our postdoctoral research fellow from CSIRO's Data 61. Take it away, Volkan.
Thank you. Can you see my screen?
Yes, we can. Thank you.
Okay, thank you very much. So in this representation of the supply chain, the technology I will present today is about automated compliance on the farm. My presentation will focus on data provenance and data trust generation components shown in this diagram. Automated farm provenance can decrease compliance costs, decrease risk of non-compliance, increase price premiums, and potentially increase the access for future markets for farmers, producers, while improving transparency and trust for consumers. Automated provenance relies on data generated by multiple interconnected devices and sources, such as smart devices on animals or devices on farm and data in the cloud. There are two very critical components that underpin automated farm provenance and compliance. The first component is data provenance. We need a record of farm data. For automated provenance, compliance, and auditing, we need to have a record of how this data is generated, stored, processed, and how it moves in the system in a traceable way. Furthermore, we shouldn't allow anyone to manipulate or tamper the data once it's recorded. And we also need reliability. So if a server fails, for example, that shouldn't cause a data loss, and we should still be able to access the data that we store. However, having a tamper-proof and reliable data record is not enough. We also need to trust the data collected from the farm. As data is generated and processed by devices and other sources which may have low accuracy or which may be faulty or tampered, we need a mechanism to evaluate how much we can trust that data. As shown in the figure, to establish data provenance, data generated by the devices on animals are collected at gateway devices, which store the data in a tamper-proof and reliable data record. But what happens if some devices generate false data? Can we use this data for automated provenance and compliance? No, data trust is a critical consideration for automated provenance and compliance. And to establish trust, we need a tamper-proof and reliable data record, but we also need a mechanism to evaluate the trust of the data at its source. So how do we do that? We are all familiar with trust in a social context. So let us consider this simple scenario. If a stranger comes and says it's 30 degrees outside, do we trust him? No, because he's a stranger, right? What happens if another stranger comes and also says it's 30 degrees outside? Now we start trusting B a little bit. And if there are more strangers confirming the same observation, we trust more. And what happens if someone we already know when trust comes and also confirms the others, we trust B even more. And the next day B comes and says it's 25 degrees outside. Now, instead of saying, I don't trust you, we can say, I trust you a little, because the previous day, he said it was 30 degrees and that observation was confirmed by others. This increase in trust can be attributed to the reputation of B that he built in time. So how did we establish trust? There might be many factors affecting how trust and reputation is built up. Evidence in forms of correlated data, observations, or events that support B improves the trust in data provided by B and also increases the reputation of B in time. Past interactions also affect data trust and reputation of data sources. A could have a direct or indirect interaction with B in the past, and these past interactions help B to build a reputation and increase trust. Going back to the farm, this slide presents an overview of our data provenance architecture. Farm data is collected from ear tags and other sensing platforms deployed in the farm or transportation devices, and then transmitted to edge devices and gateways. To achieve data provenance, a tamper-proof record trail of data is generated that accounts for the collection and processing of the data using blockchain technology. A private blockchain and distributed database are employed by the edge gateways to store distributed tamper-proof records that are also replicated to the sensor data cloud platform. The authenticity of data sources is achieved through data encryption and authentication. As you can see, our data provenance architecture is built on a few components to store data in a tamper-proof and traceable way while still preserving data privacy. The private IoT edge blockchain is built on Ethereum blockchain. It is tamper-proof, and as a private blockchain preserves the privacy of the farm data. However, it is inefficient at storing large amounts of data. Thus, we also utilize the Swarm distributed database integrated to the private blockchain. This distributed database can store any type and size of data in a tamper-proof way. To retrieve data from this database, we need the file hashes as the addresses of data packets. The sensor data cloud can store scalar vector data streams, and we can query large amounts of data. However, data stored on the data cloud can be manipulated after, so we cannot fully trust to the data that's stored on the sensor data cloud. We also use the public blockchain NRID to seal the data stored on the private blockchain for improving the security. The public blockchain is proof, however, data stored on the public blockchain is visible to all. So different components of our architecture stores different pieces of data. For reliability and scalability, we choose storing the hash of the data in a private blockchain, whereas the data itself is stored in a distributed data storage. The sensor data cloud stores raw data packets and other external data, and the public blockchain stores the block hashes of the private blockchain periodically to seal the data. Similarly, to retrieve data back, we need to follow a few steps as shown on the right. Although sensor data cloud stores device data, we cannot fully trust this data because the data on the sensor cloud can be manipulated, as I said before. That's why we retrieve data back from the distributed storage. Okay, up until here, I've explained how we store and retrieve the data for provenance. As I have said before, we require data provenance, but we need also to evaluate the trust for automated provenance, compliance, and auditing purposes. In the context of connected devices, we have agents. Those are devices or systems that interact with each other and the data produced by these agents. Trust in an agent is a belief about how likely one agent will behave in an expected way. Similarly, trust in data is a belief about how likely the data represents the truth. Similar to the trust problem that we saw before, here we have an ear tag generating some data. The gateway device receives this data, but can it trust that data? And the question is, how do we evaluate trust in farm data? Our trust service is both data-centric and entity-centric. That's we calculate trust scores for data points and also reputation scores for data sources for different data streams. Trust mechanism works at the edge layer and is implemented on smart contracts that are automatically executed when new data arrives or when a trust score is queried. To calculate trust, we first identify some trust components that we can use to evaluate the data trust. As shown here, like we have five components here: device reputation, direct trust, overhead trust, similarity trust, and multimodal trust. We first identify these trust components and then calculate them, and based on the historic data stored on the blockchain, sensor data cloud, and the new data received from sensing platforms. Finally, we fuse these components to get a data trust score by aggregating trust components with some weights. Depending on the trust score, we also update the reputation of the source for the data stream. So what are those trust components? The trust evaluation is application specific, and we determine trust components based on the application and availability of related data. So here we are looking at an example for water drinking behavior. This water drinking behavior data is provided by an activity classifier that's running on an ear tag. So for this data, we identify 5 trust components. So device, First one is device reputation. It's the reputation of the activity classifier, so it's the past history. And then we have direct trust, which is based on the consistency in previous activity reported by the platform. So if one call says, I'm drinking water, and then it says, again, I'm drinking water, we improve the trust a bit because we believe that this behavior happens in a time period. The next one is overheard trust. That's based on the messages overheard by other platforms. So if a call says, I'm drinking water, and if this message was heard by some other calls in the proximity, this improves the trust. Other component is similarity trust. That is a similar activity reported by, again, other platforms in the proximity. So if a call says, I'm drinking water, and if there are some other calls in the proximity saying that we are drinking water, this also improves the trust for this data. Finally, we have multimodal trust. This is depending on a different sensor modality. Here we use proximity to the water trough. So if a call says, I'm drinking water, and it also says, I'm close to the water trough, that improves the trust because we expect the call to be close to the water trough while drinking water. How do you calculate trust and reputation scores? After receiving the data from a sensing device, the gateway collects direct and indirect evidences, the reputation of the data source, and other related data from the blockchain, distributed database, and sensor data cloud platform. And then calculates trust components and then submits those components to a smart contract on blockchain, which then calculates the trust score for the data and updates the reputation score for the data source. So here is a simple demonstration of the evolution for trust and reputation scores for this water drinking activity. We have 3 cows, 1 water trough, and a gateway that collects data from the ear tags. So at time t0, a cow A, say, broadcasts a message saying that I'm not drinking water, I'm not close to the water trough. The packet is received by the gateway. Because it's not a water drinking behavior, we don't calculate trust for that, and the reputation is initialized to 0. At the next time instant, another cow broadcasts a message saying that I'm drinking water and I'm close to the water trough. Now, this is heard by the gateway and also overheard by the cow next to it, the cow C. The gateway, after receiving it, calculates the trust components because this is a water drinking activity. Now the trust component here is the proximity to the water trough, and based on that evidence, it assigns a trust score of 0.3. And because this trust is not very high, we don't update or increment the reputation score yet. At the next time step, cow C broadcasts a message saying that I'm drinking water, I'm close to the water trough, and I also heard the message from B at the last time. So that's received by the gateway. The gateway calculates trust for this activity. So it is now 0.32. It is a bit higher than trust for B because now we have a similar behavior that is recorded. B was also drinking water. And still the trust is not very high, so we don't update the reputation score yet. Next time instant, B says again, I'm drinking water, I'm close to the water trough. Now, this time, trust is calculated to be 0.56, and based on the proximity to the water trough, previously overheard message by cow C, and also consistent data that B provides because he or she already said, I'm drinking water before. Now, if this trust is higher than our trust threshold, we can increase the reputation of B, so the reputation is incremented to 0.2. Next time instant, cow A comes closer to the water trough and says, I'm drinking water, I'm close to the water trough. And that's received by gateway. The trust is calculated based on the similar activities of other cows and proximity to the water trough. Again, at the next time instant, A broadcasts another packet, drinking water, I'm close to the water trough. Gateway again calculates the trust based on the similarity, consistency, and proximity to the water trough. And because it's higher than our trust threshold, also increases the reputation for that data source. And finally, A moves far away and says, I'm not close to the water trough, but for some reason it says I'm drinking water. So as you remember, at the previous instance, it says I'm drinking water. Here again, I'm drinking water. So there is a consistency in the data. However, there is no other evidence supporting that data. So the trust score is calculated as 0.24 based on this, based on the previous data and the reputation. Because this trust score is now lower than our trust threshold, we decrease the reputation. So in summary, automated farm provenance and compliance requires data provenance and data trust, data provenance architecture, and also trust reputation mechanism. This has a potential impact for red meat supply chain, but it also can be applied for other agri-food chains. Thank you very much.
Thank you very much, Volkan. That was excellent, right on time. So we've got time for a couple of questions. If anyone wants to pop any on the chat, please feel free. Otherwise, I have one around the introduction that we had from Phil, where he said trust takes a long time to earn, but it's quick to lose. So when you look at your reputation scores, what do you do? Do you behave like the humans and drop it like a bomb, or do you moderate it a little bit?
Yes, so we also use the same intuition. So what we do is we increase the reputation gradually, so little by little. But if there is some malicious activity or some false data coming from the source, we decrease it like with a higher margin. So yeah, there's a difference between the increase step and decrease step.
Nice. We've had a question from the group around trust and reputation values. Are they bounded?
Yes, here we have here we bounded them between 0 and 1. That's like a metric that we use and the score range that we use. So yeah, we keep it between 0 and 1. Yes.
Excellent. Did you want to add something?
No, that's fine.
The next question I had was around the data provenance and the data trust architectures. What other parts of the supply chain could benefit from this activity?
So yes, these architectures can be applied to the other parts of the supply chain as well. Obviously, for example, logistics and the other steps of the supply chain, and that may increase the value proposition, improve the value proposition as well, because here we don't, as you can see, we don't share the data with other stakeholders. There's not much sharing here, except for the evidence or auditing reasons. So if we have other parts of the supply chain in the system, then this architecture can provide a standard data sharing platform with some access control. We can still preserve the privacy of different stakeholders, but by sharing this data in a standard form and everyone has the same view of the data, we can improve the efficiency and supply chain management as well. Plus, one of the barriers now we see is that once this system is deployed at the farm, the producers and farmers, they don't get the return for their investments back, because the value doesn't propagate back to the producers and farmers well. So if we have the whole supply chain or like bigger part of the supply chain in the system, we may actually implement some incentive mechanisms so that the farmers who invest in these technologies and architectures to get their return fair share back.
Yeah, no, that's really important, that that return on investment or the other value adds that you're getting. And the other thing that just occurred to me when you were doing the summary before around not trusting a particular animal because they weren't close enough to the water trough, at what point does the technology, like your early introduction, actually query that position? I'm just thinking if there's been, a lot of rain or something like that, and there's a new dam that wasn't identified previously that's arrived. Can you rebuild the trust because other animals are not at the water trough, but they're in a similar location?
Yes. So as you can see, we are not like giving full weight to each trust component or just single trust component. So it has multiple trust components. Each has some weights in the aggregated trust score. and that those weights can be updated, yes. And then if we update those weights, that's also recorded on the blockchain. So we know that, how we aggregate those trust components in that time as well. So that's very important, because if you are allowed to update the weights and then not store it in a temporary proof record, then you can calculate any score, right, by just playing with the weights. We don't allow that. So any trust score, it also stores the weights and how the calculation is done as well. And the parameters can be updated, yes.
Great. So we can rebuild that trust. Very important. Thank you very much, Vulcan.
Thank you very much.
I will finish and start our next